Chapter 8 is titled Stoichiometry, and it's going to take a lot of the concepts we looked at in Chapter 6 and bring them again here into this chapter, but now apply them to a chemical reaction instead of just looking at a compound. So before we start solving problems here, a couple of definitions. So when we look at a chemical reaction, oftentimes we have what's called an excess reactant. So excess means that there's essentially too much. So it is a reactant that is not fully consumed. So that means it's not fully consumed and has some amount left over. So it's in excess, it has some left over. So we also have some things called limiting reactants. So a limiting reactant will run out and is fully consumed. So that will be completely used up and there will be none of it left over. So in this chapter, they introduce what's called a percent yield. A percent yield looks at sort of how well an experiment worked out. So it compares what's called an experimental yield. So that is if you went into a lab and you actually performed an experiment and collected a product, that is compared to what should happen based off of doing some math. So experimental divided by theoretical times 100 is called your percent yield. So we're not going to see sort of any sort of real examples of this because we're not doing experiments. So this is going to be something that you'll run into a lot more in a chemistry class that has a lab associated with it. So in these sorts of problems here, this will be given to you in the problem because again, we're not running up to a lab and doing anything like that. Okay, so we're going to look a little bit at energy in a reaction as well, and we call that reaction enthalpy, and that's given the symbol delta H. So delta H is the energy associated with a reaction. So energy can be absorbed, and we have a positive delta H, and we know when energy is absorbed, that's called endothermic. And that will give us a positive delta H in a reaction. And we also have energy released, and that will give us a negative delta H, and this is exothermic. Okay, so we can have energy that's produced in an exothermic reaction, or we can have a reaction that requires energy. So we're going to talk about reaction enthalpy towards the end of this, but this is specific to a particular reaction based off of a balanced chemical equation. Okay, so to start off this chapter, we're going to revisit mole ratios. So mole ratios are looking at comparing, when we looked at them in chapter 6, we were comparing, say, our subscripts, like 2 moles of hydrogen are needed and 4 moles of oxygen to make this compound of H2SO4. We can use mole ratios in a chemical equation by comparing the coefficients. So it takes 5 molecules of hydrogen peroxide to react with 2 of the compound of potassium permanganate and 3 of sulfuric acid to produce 5 oxygen, 2 manganese sulfate, potassium sulfate, and water. 8 water. So it's telling us how many you need and how many are produced in a reaction. So we're going to use the coefficients here for this. So we're looking at the mole ratio between KMnO4 and K2SO4. So we're just looking at the coefficients. So our KMnO4 is 2. So a mole ratio would be 2 mole of KMnO4. And then if we look at K2SO4, there's no number there, which implies it's a 1. So 1 mole of K2SO4. So that means for every 2 of these we throw into the reaction mixture, we get 1 of these as a product. Okay, so next, H2SO4. So our coefficient there is a 3. So 3 mole of H2SO4. Now we're looking and comparing it to O2. So for every 3 of these, that we have in the reaction, we produce 5 of those. So 5 mole of O2. Okay, so keep going. Now we're going to go H2O2 to H2O. So H2O2, that's a 5. So 5 mole of H2O2. We look at our water. Our water has a coefficient of 8. Every 8 mole of H2O. So we have H2SO4 to MnSO4. So again, just go up here. We have a 3 mole of H2SO4. And if we look at our MnSO4, we have a 2 there. 2 mole MnSO4. And then finally, O2 to H2O. So now we're looking at O2 and H2O. These are both on the product side, which we can still do in a reaction. That means for every 5 of these that form, we have 8 of these that form. Okay, so for O2, we have a 5. So it's going to be 5 mole of O2. When we look at our H2O, that one was an 8. We're going to have 8 mole of H2O. Okay, so this is our mole ratio. So again, mole ratios for this type in a chemical reaction is comparing the coefficients. So in a reaction, we're comparing coefficients. When we were looking at a compound or a molecule, we were comparing subscripts. Okay, so for a reaction, we're comparing those coefficients. So let's even write that down. So mole ratios, these mole ratios came from our coefficients in our balanced chemical reaction. Okay, so let's start doing some problem solving using mole ratios. So given the following equation, where we have 2 irons react with 3 sulfurs to give us 1 mole of iron 3 sulfide. So we want to know how many moles of iron 3 sulfide can be produced from 14.4 moles of sulfur. So if we had 14.4 moles of sulfur, how much iron sulfate would we produce there? So this says assume that there is an excess of iron. Okay, so we're going to assume that we have plenty of iron and that there's going to be some left over. So our sulfur is our limiting reactant in this problem. So it's going to determine how much of our product we make. So you can kind of think about this like in cooking or baking. Whatever ingredient you have the least amount of determines how much of, say, something like cupcakes or meatloaf or whatever it is you're trying to make that you can make. And same in chemistry, whichever one runs out limits how much product we can make. Okay, so we're going to start with so we have 14.4 moles of sulfur. So now we're going to take our moles of sulfur. We're going to build a mole ratio between sulfur and our iron 3 sulfide. So we are solving for iron 3 sulfide, so we're going to put that in the numerator. So we have no coefficient here, so we know it's a 1. So we have 1 mole of Fe2S3. And then for our sulfur, we have 3 for every 3 moles of sulfur. So moles of sulfur cancels with moles of sulfur. Okay, and if we go, we have 14.4. 14.4. Okay, so times 1 in the numerator, and then divided by 3. So we can make 4.80 mole of Fe2S3. Okay, so for every 3 sulfurs we have, we can only make 1 of those. So we had to take this and divide by 3. And I added that 0 there because we had the 3 significant figures, so we want to make sure we keep our 3 significant figures there. Okay, so this is just going from moles to moles. So what we did here is we went from moles of compound A to moles of compound B. And to do that, all we needed to do was use a mole ratio, which was, again, our coefficients. So we did that just by building a ratio from coefficients. Okay, so using our same reaction, how many moles of sulfur are required to react with 0.546 moles of iron? So now in this one, we have this much iron, and we want to know, say, how much sulfur we need to dump into this reaction. Okay, so we're starting with our given value of 0.546 moles of iron. Okay, so we're going to build a ratio between iron and sulfur. So iron is 2. We want that to cancel. So our coefficient is 2. So 2 moles of iron. And we want to know how much sulfur we need. So we need its coefficient of 3. So 3 moles of sulfur, where iron cancels with iron. And then we're left with our moles of sulfur. Okay, so we have 0.546. Okay, so I'm going to multiply by my numerator, which is 3. I'll divide by my denominator, which is 2. So we have 0.819 moles of sulfur. That's what would be required for that one there. So we did the same type of problem here. We went from moles of A to moles of B, and we used the coefficients. So same thing here. Whenever you're going from moles of one thing to moles of something else, all you need to do is build a mole ratio based off of their coefficients. Okay, so the next problem, we want to know how many moles of CO2 can be produced from 5 moles of C4H10O and 18 moles of O2. So anytime they give you two things, so they give you an amount of one reactant, and in this problem, they have given us the amount of a second reactant here. This is what we call a limiting reagent, excess reagent problem. So one of these is a limiting reagent, one of these is an excess reagent, but they didn't tell us which was which. In the problems above, they kind of told us the limiting reagent, excess reagent, or if they only give you one value, then that's what they want you to do. They want you to start with that and solve that way. So whenever you're given an amount of one and the other of your reactants, you do need to figure that out. So what we're going to do is take this and we're going to say, if all of these 5 moles react, how much CO2 can I make? Then I'm going to take this, the oxygen, this 18 moles of oxygen, I'm going to do the same thing. Say, hey, if all 18 moles of the oxygen react, how much CO2 can I make? I'm going to compare whichever one makes the least amount of product is going to be my limiting reactant. Okay, so we'll start with 5 moles of C4H10O. So they're asking for CO2, so I'm going to take this and see how much CO2 I can make. So I have a 4 mole of CO2 for every 1 mole of C4H10O. So C4H10O cancels, and we end up with 5 times 4 equals 20 moles of CO2. So if all of that reacts, we can make 20 moles of CO2. So now let's look at what happens with oxygen. So we have 18 moles of O2. Okay, so same thing, we're going to change this to CO2 because that's the problem asked for. So we have 4 mole of CO2. And now we're going to use our coefficient of oxygen, which is a 6. There's 6 mole of O2. Okay, so we have 18 divided by 6, which gives us 3. We have 3 times 4, which gives us 12. 12 moles of CO2. Okay, so if we look at this here, if this ingredient is completely used, we can only make 12 of these. So kind of think of it as like brownies or cupcakes. If I use all, say, 18 of my eggs, I can only make 12 cupcakes. But if I use all 5 boxes of my mix, I can make 20 cupcakes. So again, we're looking, this ingredient will make less, so therefore it's going to run out. So our answer is not both of them. Our answer is just one of them. It's the one that produces less. It's our 12 moles of CO2. Okay, where we get, again, we had to do this one here so we could compare, but we take the one that produces less, and that's our limiting reactant, and that determines how much of a product we can make. Okay, so in this problem, we were using the same problem solving that we did above. We were going from moles of one thing to moles of another. So we did, again, our sort of solution map. We went moles of A to moles of B. So moles of compound A to moles of compound B. So same solution map. So we used the same technique. We used mole ratios to do that. So for that, we used our coefficients. Okay. All right, let's press on here. Okay, so of course, not everything is going to always be given to us in moles. Sometimes we're going to have to first convert into moles before we can actually use our mole ratios. So that's what we're going to see here. How many grams of potassium chloride are produced from 2.5 grams of potassium and excess Cl2? And so we have excess Cl2, so we don't even have to worry about that. We're just going to look at our potassium here. Okay, so 2.50 grams of potassium. So we're going to take our grams of potassium and we are going to convert that into moles first. So we're going to want to build a mole ratio between our potassium and potassium chloride. To build a mole ratio, first we need it to be in moles. So we have 1 mole of potassium per every, hold on, let me grab my periodic table. Okay. So if we look at our periodic table, potassium is here. Let me zoom in a little bit. So potassium is here. We have 39.0983, so we'll call it 39.1. 39.1 grams of potassium. So grams of potassium cancels with grams of potassium. Now I can build a mole ratio. So since I am now in moles of potassium, so if I look, 2 moles of potassium will produce 2 moles of potassium chloride. Okay, so we have 2 mole of potassium will give us 2 mole of potassium chloride. So now our moles of potassium cancel. So now they want us to solve for grams of KCl. So if I want to know grams of KCl, I'm going to have to turn moles into grams. And to do that, I'm going to need to multiply this by the molar mass. Okay, so we have 39.1. Oops, let's go turn the thing on. 39.1 is the molar mass of potassium. Chlorine is 35.5. So for every 74.6 grams of KCl, we have 1 mole of KCl. So moles cancels with moles. Okay, so now I can punch all of this into my calculator and I can solve. So 2.50 divided by my 39.1. Okay, I'm going to take that and multiply it by 2. I'm going to take that and divide it by 2, so my mole ratio here. And then I'm going to multiply by 74.6, which was my molar mass of KCl. When I do that, I get 4.77 grams of KCl, where 3 sig figs here tell me I need 3 sig figs here. Okay, so this one, a little bit more complicated. We still essentially did the same thing, moles, mole ratio. But before I did that, I had to turn grams into moles, and then they asked me for grams at the end. So I used some of my chapter 6 skills where I know to go from grams into moles, I divide by the molar mass. And once I have something in moles and I need to know the mass of it, I multiply by the molar mass. So this solution map, a little bit more complicated. So this one we went from mass of compound A, then we went to moles of compound A, then we used a mole ratio to get moles of compound B, and then we went to mass of compound B. So this one required us to do 3 steps. So each of those arrows is a conversion factor, essentially, that I needed to accomplish this problem. So when I'm going from mass of moles of any sort of compound, I use the molar mass. When I'm going from moles of one thing to moles of the other, I'm using the coefficients. And then when I'm going from moles of something back to mass, I'm going to use the molar mass again. Okay, so we're just using the molar mass of our different compounds and our coefficients from our chemical reactions to do these types of problems. Okay, so I'm going to do kind of a sub part of this because I do want to kind of talk about what's happening here. So my sort of we'll call it 4B. So 4B, I'm interested to know what mass of Cl2 was used in this process. Okay, so what mass of Cl2? So there are 2 ways you could go about this problem, and I like to kind of show this as we're working through this here. So you could set up, if you want to know what mass of Cl2, you could take your 2.5 grams of potassium, turn it into moles, build a mole ratio, take your molar mass, and solve for grams. That will work. But I do want to kind of note that we can use a little trick for this problem here. So if we look back at our reaction, we know that 2.5 grams was used here, and we know that in the reaction we produce 4.77 grams here. So the difference between these two has to be the Cl2 that was used. So we're going to kind of use the law of conservation of mass to kind of help us solve this problem. Okay, so we know that the mass of reactants has to equal the mass of the products. Okay, we didn't create matter, we didn't destroy matter, all we did was rearrange it. And this only works for mass. Moles can be a different story because you can break things apart and form things to more complicated structures. So this only works for mass. So we're using the law of conservation of matter, which is mass. Okay, so we have 2.5 grams of potassium plus X grams of Cl2. We know that that has to equal 4.77 grams of KCl. So our mass of Cl2 then has to be at 2.27. So 2.2, we'll call it 7 grams of Cl2. Okay, so 2.27. Okay, so if we add that and that, we should get this, which we do. 2 plus 2 is 4, 5 plus 2 is 7, and then we get the 7 there. Okay, so we combined a mass of potassium with a mass of chlorine to get the mass of KCl. So we just, again, use the law of conservation of mass for this problem here. So you're going to encounter a handful of problems as you're working through Chapter 8 where you can use this. So again, if you know the masses of things in your reaction and you're solving for the mass of just one thing that's missing, you definitely can use this here because it has to work. It's the law of conservation of mass. Okay, so we're going to do one of the same type of problem. Okay, so we have a chemical reaction. We want to know how many grams of sodium chloride are produced when 80 grams of O2. Okay, so we collect 80 grams of O2. We want to know how much sodium chloride we also collect in the process. So we have 80 grams of O2. Okay, we're doing essentially the same thing we did above. We're going grams of oxygen to grams of NaCl. So our solution map will be exactly the same. We're going to go from mass to moles by dividing by the molar mass. We're going to go from mass of oxygen to mass of sodium chloride by using the coefficients. And then we're going to take moles of salt or sodium chloride to mass of sodium chloride using its molar mass. Okay, so to turn this into moles, so we have 1 mole of O2 divided by 32.0 grams of O2. Okay, so since we have 2 oxygens there, we multiply the molar mass of oxygen atom, which is 16, by 2 to get 32. So now we need a mole ratio. Okay, we're solving for NaCl, so we're going to use its coefficient of 2. So 2 mole NaCl. And then we need to get rid of the moles of O2, so we're going to divide by its, which is 3. 3 mole of O2. And then finally, we need to convert this to grams. So we're going to put the molar mass of NaCl there. So sodium is 23. And our chloride is 35.5. So we get 58.5. Okay, so if we look, grams of oxygen cancels with grams of oxygen. Moles of oxygen cancels with moles. Moles of sodium chloride cancels with moles. And we're left with the mass of sodium chloride. Okay, so let's put it in our calculator and solve. You don't want to, there we go. We have 80.0. And divide that by 32. Multiply by 2. Divide by 3. And then multiply by our molar mass of 58.5. And we get 97.5 grams of NaCl. Okay, so there we are. Okay, so this is a problem where we could do what we did above. Okay, so we know the mass of oxygen produced, we know the mass of sodium chloride produced. So because we know both of these, we do know the mass of sodium chlorate we started with. So if we combine this mass with this mass, we will get the starting mass of sodium chlorate we use. So the 97.5 plus our 80 means that we started this reaction with 177.5 grams of the sodium chlorate, which this problem doesn't ask us for, but I did, again, want to reiterate that the mass on this side always has to equal the mass on this side. Okay, so move on. So problem 6 is looking at, we have 60 grams of silver nitrate combined with 10 grams of nickel. What's the theoretical mass of silver that can be produced? Okay, so we have 60 grams of silver nitrate, which is this here. And we have 10 grams of nickel, which is here. And we want to know what mass of silver we can produce. So this one says theoretical mass. What theoretical mass means is calculated mass. So everything we've been doing so far, those were all theoretical moles and theoretical mass, which means if this reaction obeyed 100% perfectly, this is what we could collect or accomplish. Okay, so since we have 2, we're going to have to do the limiting reactant excess reactant comparison. So I'm going to take this and solve for silver. Then I'm going to take this and solve for silver. I'm going to see which one of those two will produce less. And that's going to be my theoretical mass of silver. So we'll start with the 60 grams of AgNO3, or silver nitrate. Okay, so our solution map is the same as we've been doing, grams to moles, mole ratio, moles to grams. So we have 1 mole of AgNO3. Okay, so our molar mass of this guy, let's see, silver is 107.9. Okay, then we have 1 nitrogen, which is 14.0. And then we have 3 oxygens, which are 16. So we have 169.9. Okay, so that cancels there. Now we have moles of AgNO3 that we started with. So now we're going to make a mole ratio. So again, we are solving for silver. So we get 2 moles of silver because our coefficient is 2. And we have 2 moles of silver nitrate. And then finally, it's asking for mass, so we can do that last step there and do our molar mass, which was the 107.9 grams of silver for every 1 mole of silver. Okay, so now our moles of silver nitrate cancels, our moles of silver cancel, and we're just left with our mass of silver. Okay, so we have our 60 divided by the 169.9. Oh, that's right. Okay, 60 divided by 169.9 times 2 divided by 2, and then times the 107.9. So if all of this reacts, we can get 38.1 grams of silver. Okay, so we're not quite done yet. You could box this answer and put it into Canvas and you'd have a 50-50 shot. We do need to now compare it to this. If all of this reacts, we need to see how much silver this will make. So we have 10 grams of nickel. Okay, so 1 mole of nickel for every, so nickel is 58.7. Okay, so looking now at a mole ratio, that 2 is still the same. So 2 mole of silver. Now we only need 1 mole of nickel. So 1 mole of nickel. And then we want to convert this to mass, so this is the same. So the 107.9 grams of silver for every 1 mole of silver. So if we go through and make sure our units cancel, grams of nickel gone, moles of nickel gone, moles of silver gone, just left now with mass of silver. Okay, so let's plug this one in now. So 10 divided by our 58.7 times 2, divide by 1, and then times 107.9. So if all of this nickel reacts, we would have 36.8 grams of silver. Okay, so we solved both of those independently. Now we get to compare. So if we look, the nickel actually produces, almost 2 grams less silver than the silver nitrate does. So our nickel is our limiting reactant. So the lesser amount that is produced by our 2 products is going to be our theoretical mass. And again, we chose it because it was the less amount. Okay, the less amount. So after doing this, we have now our theoretical mass. Okay, so this one is now asking us to do a nice percent yield for this reaction. So if we went into a lab and we ran this reaction and we were able to collect 28.2 grams of silver, what's our percent yield? So this is the experimental. So that's going to go in our numerator. So we have 28.2 grams over our 36.8 grams times 100%. Okay, so experimental, theoretical times 100. So let's see how they did. 28.2 divided by 36.8 times 100. So we have 76.6. So they collected 76.6% of the mass of silver that theoretically could have been produced. They could have gotten a maximum of 36.8. They got the 28.2, so they got 76.6% of the silver from the process. Okay, so now this last part here, asks what mass of the excess reactant is left over. So the nickel was our limiting, so they want to know of this 60 grams of silver nitrate that we had, how much of it is now left over. Okay, so kind of, I'm going to put a little bit of a definition here that we're going to use for us. Okay, so we have the initial amount. So we have the initial amount of whatever it was in our reaction, in this case, the silver nitrate. So the initial amount is going to equal what's used in the reaction and what's left over in excess. Okay, so some part of that 60 is going to be used in the reaction and some part of it's going to be left over in excess. So for us solving this problem, we know that initially we had 60.0 grams of the AgNO3. Okay, so we're going to be solving for the excess, so that's X. So there has to be a way for us to solve what was used in the reaction, and it turns out there is a way. We're going to use stoichiometry to see what was used. Okay, so we're not just going to take the difference between these two. It doesn't really work that way. We have to actually calculate what was used in the reaction and now what is left over. Okay, so it involves one more stoichiometry setup. So we know 10 grams of nickel were used in the reaction. So I'm going to pull my 1 mole of nickel per every 58.7 grams of nickel from above. Okay, so now I want to know how much of the silver nitrate reacted. So if I look up here, 1 mole of nickel requires 2 moles of silver nitrate. So 2 mole of AgNO3 for every 1 mole of nickel. And then finally, mass. So we already calculated that molar mass above. That was 169.9 grams of AgNO3 for every 1 mole of AgNO3. So it's like, oh my gosh, we had to set up a whole nother stoichiometry problem. We did, but luckily all these bits of information we already had from when we did this up here. So I just pulled this and this from up here, and all we really had to do was build a new mole ratio. Okay, so let's solve. Okay, so we'll clear this. We have our 10 grams of nickel divided by its molar mass of 58.7. times 2 for our mole ratio here, and then times the molar mass of 169.9. So we have 57 we'll call it 9 grams of AgNO3. Okay, so if we go back up here, so now this is what's used in the reaction. So this is used. So now I can put this up here as my 57.9 grams. So I had 60 grams of start. I used 57.9 in the reaction, so I want to know what's left over. So I'm going to take my 60, and I'm going to subtract my 57.9, and I have 2.1. So X there equals 2.1 grams of AgNO3 left in excess. Okay, so that's what was used or not used in the reaction that would have been left over in the reaction there. Okay, so again, I kind of want to note from above, it's not just the difference between these two. We have the 38.1 subtract the 36.8. See, not the difference of those two there. Okay, so what's left in excess, you actually do have to solve with stoichiometry. You can't just subtract these. That's not what it is. Again, we can figure out what was used in the reaction just by using stoichiometry. So now this is what's left over after the reaction happens. Okay, so in this chapter, this would be one of the more difficult ones you would have to do. where you have a limiting reactant and you have to figure out which one is your limiting reactant by solving for which one is going to run out first. Have a percent yield, and then obviously this part here is really what makes this a little bit more difficult. When you have to solve for the mass of excess, again, you know initially what you have that's given in the problem. You do have to do more stoichiometry to see what's used in the reaction. And then the difference between these two is going to be what's left in excess. Okay, so to finish this, finish up chapter 8, we're going to look at energy. Okay, so reaction enthalpy. So kind of we just defined this on the first page. We have endothermic, where energy is absorbed, and we see this with a positive delta H. So delta H for this reaction is 66.4 kilojoules. And then we have exothermic, energy is released. So this delta H is negative 486 kilojoules. Okay, so how this works is this energy is specific to the coefficients of this reaction. So we can build mole energy ratio. So that's what we're going to kind of do here to start. So for example, for every 1 mole of N2 that reacts, it's required 66.4 kilojoules of energy to react. Or we can say for every 66.4 kilojoules of energy absorbed, 2 mole of O2 would be required in the reaction. So kind of like mole ratios, but we're putting energy in there. So this is similar to moles, 2 moles and 66.4 kilojoules of energy. Okay, so if this wasn't a 2, this was a 1. If we had like a 1/2, 1, 1, then this would be half of that as well. This would be 33.2. So this energy is with these coefficients here. If these coefficients change, so does that energy. Okay, so same thing here. The only difference is we use the sign to show if energy is coming into the system, positive, or energy is going out of the system, negative. So same thing here. We could say for every 2 mole of H2 that react, 486 kilojoules of energy are released. Or we could say something like, when 486 kilojoules of energy are released, we know that 1 mole of O2 reacted. Okay, so same thing. Only difference is we're going to have our negative sign in there to show that it is exothermic. Okay, so the first one, how much energy is absorbed when 6.75 moles of O2 react in the endothermic reaction above? Okay, so we have 6.75 moles of O2. So we're going to use our ratio and we're going to solve. So I have this one actually written out for us here. So we're solving for energy. We want that in the numerator. So we have the 66.4 kilojoules of energy. And when that reacts, it requires 2 mole of O2. 2 mole of O2. So moles of O2 cancel, and we're left with our energy that would be required for this reaction. So 6.75 times 66.4 and then divided by 2. So 224.1, 3 sig figs, we'll call it 224. So 224 kilojoules of energy would be required to react 6.75 moles of O2 in that reaction above. Okay, so number 2, how much energy is released when 5.56 grams of H2 react in the exothermic reaction above? So now we're looking at this one here. So now we're not given moles, we're given grams. That's okay. We know how to turn grams into moles. So we have 5.56 grams of H2. So we have 1 mole of H2. Let's see, what is hydrogen? Hydrogen is we'll call it 0.1. So we'll have 2.02 grams of H2. Okay, so grams cancels with grams, and we're left with moles. So now we're going to build a mole ratio between hydrogen and energy. Okay, so our energy, 486. And now we need to know how many moles of hydrogen that corresponds to. So our coefficient is 2. So the 2 mole of H2. So it was just this conversion factor here that I had to do the reciprocal of to get the energy in the numerator and the moles in the denominator. So moles of H2 cancels. So now let's look at what sort of energy we would release with this. So 5.56 divided by 2.02. So there's our moles of H2. So times negative 486, that's our energy. And then we're going to divide that by for every 2 moles of H2. So let's see, 3 sig figs will have negative 669 kilojoules of energy. Okay, so we do have the negative sign because it is exothermic, but a lot of times if they tell you released or if they tell you it's exothermic, a lot of times they will accept, like in Pearson, they will accept that 669 kilojoules of energy were released. Released equals the negative sign, so it's almost redundant if released was in there to include the negative sign. So oftentimes they'll accept the positive of this so long as the word release was in the question. Okay, so last one. If 23.5 kilojoules of energy are absorbed, how many grams of nitrogen reacted in the endothermic reaction above? So I'm just going to rewrite this real quick. So remember that was N2 plus 2 O2. That produced 2 NO2. And the delta H was 66.4 kilojoules. Okay, so now we're going to do essentially the same thing, but now we're starting with energy and working our way to grams of nitrogen. So we have 23.5 kilojoules. Okay, so if we look at this reaction, the energy required for this reaction is 66.4, so that's going to be down here. So that's going to end up canceling with that. And they're asking us to solve for mass of nitrogen. So we're going to use this and the coefficient of nitrogen, which is 1. So 1 mole of N2. So our energy cancels. We now have moles of N2. And now they're just asking us to turn that into grams or mass. So that's going to be 28.0 grams of N2 for every 1 mole of N2, where our moles of N2 are going to cancel there. Okay, so we have 23.5 divided by 66.4. Okay, so times 1, which was our coefficient in our reaction, and then times by the mass of nitrogen, times that 28. So we get 9.909, all those other numbers there. So if we look, we have 3 sig figs here. So it looks like we're going to have 9.91. So if this amount of energy was absorbed, then that amount of nitrogen reacted in the reaction. Okay, so again, this last part kind of taking our discussion of energy that we started in chapter 3 and started applying it to chemical reactions. So some chemical reactions release energy. That's very useful because we can use that to heat our homes and power our vehicles and all that sort of thing. And then some reactions require energy. Okay, so this one here required energy. So that means these were at a lower energy state, and to force them into a higher energy state, we had to pump energy into the reactant for that to happen.